Where's my pen for my tablet? Okay, I found it. Okay, so let's talk about the Stefan-Boltzmann's law. So the Stefan-Boltzmann's law describes how thermal radiation emitted by a black body in a thermal equilibrium is related to its temperature. The law is named after Joseph Stefan and Ludwig Boltzmann, who discovered and derived it respectively. Okay, so here's some theory for the Stefan-Boltzmann's law that you should probably know, where we see how it describes the radiation emitted by a black body. Very important, the word black body in this case. We'll talk about what a black body is now. So a black body would be some spherical object, which, let's say radiation, it absorbs 100% of the radiation and it re-emits 100% of the radiation. Okay, so it's a perfect emitter. You can think about it that way. And then let's see what emissivity is. Emissivity is a dimensionless quantity in the measure of how efficiently a material emits thermal radiation compared to an ideal black body. Very important. Okay, so in this case, let's continue reading first. The emissivity of a material ranges from 0 to 1. A higher emissivity indicates that thermal material emits thermal radiation more efficiently, while a lower emissivity means it emits less efficiency. The emissivity of a material can depend on factors like temperature, wavelength, and the angle of incidence of the radiation. A little bit of law of reflection. Then we have this is according to Google. I did a quick little Google search and just posted it on, or pasted it on this application. So the emissivity of most natural Earth surfaces is it's unitless quantity, and it ranges between approximately 0.6 and 1. Okay, so what does this mean? Well, let's say, for instance, we have some, which is usually referred to as a gray body. So let's say we have 0.3 emissivity. Now, in our Stefan-Boltzmann's law, we're going to add this 0.3 to our equation, which has 0 units. Okay, so no unit. So we can just simply add 0.3. So let's talk about what is the Stefan-Boltzmann's law in a calculation. Well, we can state it as P, which is equal to the Stefan-Boltzmann's constant multiply the area multiply temperature raised to the 4th. So what exactly is this P? Well, the P is, you can sort of think about it as the power. Okay, I'll quickly go into detail. So it's more of the power that's radiated per unit area. Okay, if you really want to be fancy. And this would be measured, or the unit would be what? Then we have the Stefan-Boltzmann's constant. Now the Stefan-Boltzmann's constant is 5.67 multiplied 10 to the power of negative 8 watts per meter squared per Kelvin raised to the 4th. Now you should make some connection. Meter squared, Kelvin raised to the 4th. I can see, well, my temperature here is raised to the 4th, so we can just assume that my temperature is going to be measured in Kelvin. Why is that? Because my 2 Kelvins need to cancel out. And then we have our area of a spherical object. So the area can be rewritten as 4 pi r squared, which is the surface area of a sphere. Okay, of a sphere. So let's add area. T is for temperature. And now we just plug in our values and we can solve equations given. So let's look at one example. So I have an example down here. Okay. So a spherical body has a radius of 0.5 meters and a temperature of 600 Kelvin. Calculate the total power radiated by this black body. In the following video, I'll do some calculations with emissivity. So let me actually quickly go back to this. So let's say we're given emissivity as well in some examples. Then we can just simply say, well, the power is equal to the emissivity multiplied the Stefan-Boltzmann's constant, multiply the area, multiply the temperature raised to the 4th. As I mentioned before, the emissivity has no unit, so you'd simply just add 0.3. Or let's say they talk about, well, 30% of the radiation gets absorbed or emitted. And then we can simply say, well, 30% is equal to, so we can say 30. And we can multiply this with 100%. A very simple equation where we have 30 over 100, and then we have 0.3. Actually, no idea why I just said 30% times 100%. Anyway, let's go back to this one. So spherical body. Interesting. Spherical body. Okay, a sphere has a surface area of 4 pi r squared. It's worth mentioning that It's not perfect spheres, but spheres come closely comparable to celestial bodies, right? Very closely comparable. Has a radius of 0.5 meters. Okay. And a temperature of 600 Kelvin. Okay, so let's write down our Stefan Boltzmann's law. So P, so we're calculating for power in this case, okay? The power radiated by this black body. So we know that our final answer should be in watts, since watts is a unit of measurement for power. Then we have, in this case, it's a perfect black body. And where students get confused is sometimes they try and look for an E. So a perfect black body has an emissivity of 1. I forgot to mention this, my apologies. So let's say, for instance, we have the Stefan Boltzmann's constant, but Stefan Boltzmann's law, but we replace the emissivity with 1. So obviously, therefore, anything multiply 1 is whatever it's multiplied with. So in that case, we don't need to write it. Okay, so let's write the Stefan Boltzmann's constant, multiply the area, multiply the temperature raised to the 4th. So therefore, the Stefan Boltzmann's constant is 5.67. This is worth noting. Multiply 10 to the power of -8. And we're going to multiply this with watts. And we can say, I can substitute this. Or let me do the full equation first. And then I can show you how to rearrange it. Multiply m to the power of -2. Multiply k to the power of -4. And then they say we have, this is going to be my first equation. My second equation will then be, we have a radius of 0.5 meters. So now we can say, well, 4 pi r squared. R is my radius. What exactly is my radius? Let's say we have a sphere, some center point to the edge inside my sphere. And we have some center point to the edge. That would obviously be the radius. If we need to find, if we're given a diameter, we can simply say, well, the diameter is equal to, or 2 divided by the diameter is equal to radius. So we can rearrange this formula to say my diameter is equal to 2 times my radius. Okay. Yeah. So, and this is in, sorry about this. I need to cancel out my parentheses. Meters squared. And then we have our temperature, which is given as 600 Kelvin raised to the 4th. Okay, so let's simplify. Well, yeah, I can see. I'm going to first take all my values from my denominator to my numerator. So we have 5.67. This I'm going to move to the numerator to create a positive exponent. So 10 to the power of 8, we're going to multiply with watts. I'm going to do the same thing here, move from numerator to denominator, vice versa. I just mispronounced that one. K to the 4. Okay, so that's used, and used. So 4 pi r squared, well, what is 0.5 squared is 0.25. 0.25 I can rewrite as 1 over 4. And then I can multiply the 1 over 4 with 4, which simply gives me 1. So I'm therefore left with pi times meters squared. And in this case, we have 600 raised to the 4th. So 600 raised to the 4 and Kelvin raised to the 4. Okay, let's do some calculations. Also cancellations. Excuse me. Cancel. Oh, it's very important to note that area, you should know this by now, is always in meters squared. While sometimes this would be given in centimeters. So what you then have to do is you have to multiply it with 10 to the power of -3, right? To go from meters to centimeters. Or you can just take your centimeters value and can divide by 1,000. It's the exact same thing. But for scientific communication, you want to use scientific figures or might be known in mathematics as scientific notation, 10 to the power of -3. Okay. So now look at that. We're left with watts. So it makes perfect sense, right? So let me get my little calci. So in this case, I'm going to say 5.67. We're going to multiply this with 600 raised to the 4th. And I'm going to divide this in one equation. So parentheses 6.776. And I'm going to multiply this with pi. Ooh, I forgot my pi. And 600 raised to the fourth. And I'm going to divide this by 10 to the 8th power. So and therefore I'm going to use my approximate value. So I get approximately 23,085.4 watt. I guess we can just write 23,085 watt. So now we calculated the total power that's radiated by this perfect black body. Now the only thing that might change in these type of equations is that some emissivity might be given. Okay, so some emissivity might be given, and then we can just add it into our equation with no unit. Okay, it'll have no unit. Since it's a percentage based value, it has no unit, so we can just take it from percentage to decimal. Now I ran out of blackboard. How can? Okay, so let's quickly look at this. E, Stefan Boltzmann's constant, and this is for, you use this for with a topic that's known as gray bodies, where we have some emissivity. Okay, so let's rearrange to solve for T in this case, because that's usually the one students find a little bit difficult. So how I can rearrange to solve for T is I can divide both sides by emissivity, Stefan Boltzmann's constant, and area. Okay, so I get then that T to the fourth is equal to the power radiated over emissivity times the Stefan Boltzmann's constant times the area. Now I can fourth root both of these equations. And what you might notice is that sometimes the form, you might write the form P over E Stefan Boltzmann's constant A. You might write it in this form, but in most physics textbooks, you will see this. And we're going to raise it to 1 over 4. Okay, we're going to raise it to 1 over 4. This is a very important exponential rule that you need to be familiar with. We can write this as, let's say we have the square root of x to the first power. So in this case, we just have x 1 over 4. And the exponential rule looks like this, BA. So whatever value you have over here is going to be as my numerator of the exponent, and the value you have over here will be as my denominator. And then you can just add your variable that's given. In this case, we have 4 different variables, 2 constants, 2 variables. But very important to rearrange raised to the 1/4 power. I think you might get some credit points if you do this. Not necessarily credit points, but it will show the teacher that you're not really using mathematical methods. I mean, of course, it's mathematically related, but for scientific communication, raised to the 1/4 looks way better than this fourth root of some variable. Okay, just a little tip. Anyway, see you around.